In one of my previous videos, I talked about the Conformal Cyclic Cosmology hypothesis by Roger Penrose. It describes an alternative explanation for the rapid expansion we see right after the Big Bang by proposing a cyclic universe that repeats in aeons, which are the expansion we see at 10 to the negative 35 seconds. Besides it just being a hypothesis for now, there are some promising observations in the CMB in terms of so-called Hawking points. Though some scientists really seem not to be okay with that, but that's totally fine. I was pretty clear in my last video that I certainly support the hypothesis of CCC and oppose the inflation theory that contradicts CCC. But recent events in politics and in general in society reminded me of a core belief that we as scientists believe in. The way we work and think, the way we make progress. A scientist's most ambitious undertaking shall be trying to disprove their own beliefs. Only if we find out that you were wrong, it results in progress. This is how we learn. So I decided to revisit inflation theory and try to find a reason that makes inflation appear more correct than CCC. And for that, we need to understand inflation in the first place. And that's what we are going to do in this video. So buckle up and get ready for some rapid expansion, y'all. First of all, what are we talking about when we say inflation theory? Inflation is a component or extension of the Big Bang theory. It describes what happened between 10 to the negative 37 and 10 to the negative 35 seconds. The Big Bang theory in its original form showed some issues as humans continued measuring the universe and realized that the expansion of the universe is much faster than previously thought. We will go into more detail in a bit, but in short, inflation tries to describe or explain the following two issues. The uniformity problem and the flatness problem. It was developed by particle physicist Alan Guth around 1980 as of today it's our most accurate model to describe the universe. It does not explain why the universe banged in the first place, but it tries to explain the expansion process in the early universe without causing previously mentioned problems. Now, to the explanation part of this video. Let me give you a quick recap to jog your mind when it comes to the Big Bang theory. The Big Bang theory, contrary to common belief, does not actually describe the bang or creation of the universe, if you will, but rather the process of expansion. The Big Bang theory only says that the universe is expanding, but with that come some conflicts related to observations, in particular one famous observation in the universe that no matter what direction you point your X-ray telescope, space-time appears to be the same no matter where you look. Now, that doesn't seem to be that impressive. In fact, it is actually quite boring if you think about it. I mean, it would be definitely cooler if there would be some sort of glowing nebula that bends space-time and makes light bend and time slow down and stuff like that. Well, that's actually what space-time does. But in physics, it is still considered to be uniform. Because on the large scale, and I mean space-time large, the universe is the same everywhere. But the light bending thing comes in actually quite handy. Remember that this whole concept is based on Einstein's theory of general relativity. Consider pointing your telescope on Hawaii straight up. You observe the light that traveled roughly 13.8 billion years from the border of the observable universe towards you. You study it, measure it, and find out that it appears to be identical with our solar system in terms of physical laws, distribution of energy and matter, and in general everything else. But granted, our solar system and the far corner of the universe are connected and information can travel back and forth, and that's what is necessary in physics, for something to become uniform. It has to be in contact with each other. Now, consider taking a flight to the exact opposite of the Earth, of where you just were. You now point your telescope straight up again and look, geometrically speaking, at the exact opposite side of the universe, of the observable universe. You once again study and measure the far corner of the observable universe and find out that it also is quite uniform with our galaxy. Not surprising, right? Not too fast, literally, because even though it makes sense that you are uniform with each of the far corners of the universe, those two far corners that we observe have never been in contact with each other. Light that we observe from one corner by definition has not yet traveled to the other corner of the universe. And as photons are the fastest way of communication, we prove that both corners are not aware of each other. So how can they be uniform? Well, the only explanation is that they at one point were close enough to be in contact. But that's what we already suspected, right? The universe is expanding, and according to the Big Bang Theory, was at one point, well, an infinitely dense point in space-time that could have therefore become uniform. Problem solved. So why the need for inflation here? Omega. No, I'm not talking about the watch manufacturer. In cosmology, we use omega for the mass density of the universe. If you can't wrap your hand around what that means, think about it as how close one piece of matter is to another one. So, in other words, how dense is the matter in the universe? As we know from Einstein's E = mc squared, mass is just a form of energy. We can calculate omega through observation, and as of right now, 13.8 billion years after the Big Bang, omega appears to be close to 1. And that means that spacetime is flat. And in this case, flat does not mean Euclidean flatness of a two-dimensional plane, but actually a flat four-dimensional spacetime. So far so good. If we roll back the clock through the expansion rate in the Big Bang Theory, we can calculate omega at the CMB. And here comes the problem. Omega doesn't just tell us about the geometry of spacetime, it also tells us about the expansion behavior of spacetime. If omega is exactly 1, then spacetime stays the same. It doesn't expand, nor does it collapse. If omega is more than 1, spacetime is open, like a saddle, and would have expanded so fast that no galaxies would have been able to form. If omega is less than 1, spacetime is closed like a sphere, and it would instantly collapse into a giant black hole of the size of the universe itself. Remember, we can calculate omega at the time of the CMB, so very shortly after the Big Bang. Now, the last time I checked, spacetime has expanded from the size of the CMB, and it also is not a giant black hole. But we also have galaxies, so what the heck? It shouldn't work with any number of omega. But what we find is that omega at 10 to the negative 32 at the CMB is actually slightly above 1. Therefore, for the universe to be able to become uniform before the CMB, it must have expanded in such an incredibly high velocity at the Big Bang that the Big Bang Theory does not predict. And that is what inflation does. It assumes that the universe was in a very special state at the time of creation, whatever that might be. The stuff in the universe at that time was insanely hot and dense, and at that time, the universe was the size of the billionth of a proton. At that size and energy density, the universe would have become uniform virtually instantaneously. But the state of the universe caused gravity to produce a reverse effect. Instead of attraction, it would create repulsion. This caused the universe to exponentially expand in size. Every 10 to the negative 37 seconds, the universe doubled its size. For inflation to work, it must have doubled at least 100 times, which is actually not that much. Towards the end of inflation, the Higgs mechanism turned on, and energy was converted to mass. Nuclei formed, which created the default gravity effect of attraction, ultimately ending the process of inflation. It is important to note that the energy density remained the same. Energy was literally created. Now, that seems to conflict with the law of energy conservation, but it actually doesn't. As we know, energy can be both positive and negative. Similarly, how a photon can spontaneously turn into a positron and electron pair, which have both opposite charges and totaling a net zero. In the case of inflation, the increase in energy is offset with the increase in gravitational energy, which has a negative energy. Altogether, inflation does give an explanation to the two problems that come with the conventional Big Bang theory. Now, there are many more parts to this, considering general relativity, quantum fluctuations that result in slight energy density differences in the CMB to an extent of 14 decimal points, and the problem with the special state of matter causing gravity to turn on its head. Alan Guth himself regularly says that he's amazed by the accuracy of inflation, or that inflation predicts, and that even though inflation might not actually be what or how the universe expanded and how it happened, it is astonishing how complex the universe is and how far we got in explaining how the universe works. No matter if you like the idea of inflation or not, you can't argue against its surprising congruency with observations. I definitely recommend you watch the interview with Alan Guth that I linked in the description to hear the man himself explain it to you in his own words.